Hello, I'm Michelle Davis of the Center for Manufacturing Research at Tennessee Tech University in Cookeville, Tennessee. Welcome to the Fall 2020 Golden Eagle Additively Innovative Virtual Lecture Series. This is the 10th semester we have produced this popular and informative series. The series is hosted by TTU's Center for Manufacturing Research and the iMaker space at TTU. Additive manufacturing is a focus of both entities, and as such, this short virtual lecture series has been planned to highlight the best practices, potential problems, technological advancements, innovations, and scientific contributions in additive manufacturing, with expert talks from various institutions, industries, R&D centers, and laboratories. Today, we are honored to hear from Olaf Diegel, professor at the University of Auckland in New Zealand. His talk is titled Design for AM, the Key to Industrialization of AM. The speaker will provide his contact information for questions after the presentation is over. Thank you, and I turn the presentation over to Olaf.
Thank you, Michelle, and good morning, everybody. It truly is a pleasure to be talking to you all from, well, literally the other end of the world. And as always, the first challenge is going to be to share my screen. There we go. That should hopefully take care of that. So, yes, good morning, all. My name is Olaf, and I'm going to be talking to you guys about a topic I'm very passionate about this morning, which is design for additive manufacturing. But before we start, a bit of background about who I work for. It's the University of Auckland, but I head up an outfit called the Creative Design and Additive Manufacturing Lab, which is a bit of a mouthful. But I effectively describe it as a playground where companies, students, people off the street can come in and experience additive manufacturing, have a bit of a play with the technologies to see what they can do with it and how it can help them in their businesses. So that's what it's all about. We work very closely with our makerspace as well. So it's almost like the makerspace 2.0 for the next level when you want to go into the industrialization of additive manufacturing. Today, really, the take-home messages for you guys is why and when to use additive manufacturing. And really important takeaway is that not everything should be 3D printed. It's great for some things if it adds value. If not, it's probably the most expensive manufacturing method in the universe. So knowing when to use it for the right reasons, and for that to work, you really have to design for it. If you come with a conventionally designed part, designed for machining or injection molding and print it, yes, it can be done, but it'll give you a mild heart attack when you get the price for it. So learning how to design for it the right way is absolutely critical. So I guess, the first question is, the reality today, additive manufacturing, how good is it? Can it be used for manufacturing? In many cases, absolutely yes. In all cases, definitely not. So again, understanding what the reality is important. For me personally, I always think of additive manufacturing, and that's both metal and plastic, in the same way I think about sandcasting. If you think about sandcasting, the surface finish of sandcasting is relatively rough. It's a surface of the sand that's used for the mold. If you think about additive manufacturing, the same way, you will not be disappointed. So I've got a picture of an engine block there, which is a perfect example. 90% of the engine block, you don't care about the surface finish, so you just leave it the way it is. But anywhere where you need engineering tolerances or good surface finishes, you'll bore the pistons, you'll skim the heads. Anywhere we have bearings, you'll actually machine that to get it to the right tolerance. Additive, exactly the same. And a really good example of that, this is from Formnext from 2 years ago, an Audi engine block printed. And you can see the front row of pistons has been bored out to make it nice and smooth. The back row of pistons is as it comes off the machine. If you tried to run pistons in that, they'd grind themselves to death in a few minutes. So yeah, the reality is it's definitely usable, but you need to understand the parameters through which you can use it. So the next question becomes, well, why is everybody so excited about additive manufacturing? Why is, it's a hot topic now and anything to do with additive manufacturing? I guess the answer is fairly simple: growth. The growth has been 20 to 30% over the last decade. Unbelievable growth. And it doesn't look like it's going to be slowing down. Even with COVID, it may not be slowing down all that much. But by and large, in my opinion, that growth is driven by the big boys. Siemens, GE, all the big companies putting big money into it. There's still not many SMEs you can walk in today and see them using additive manufacturing for real manufacturing. And the simple reason is because it's slow and expensive. So understanding, again, to repeat myself, where, why, and when to use it is really important. and it's not a replacement technology for conventional manufacturing. And that is really important. In my opinion, even looking 10 years, 20 years down the track, I don't think additive will ever replace conventional manufacturing. It's a complementary technology that, if you use it for the right reasons, gives you enormous advantages, and that's when you want to use it. And again, repeating myself again, not everything should be printed. So it always becomes an equation of the value of the part versus the cost to make it. So going through some of those advantages, and the best known of which, of course, is complexity. Complexity, the more complex the part is, the better suited it is to additive manufacturing. One of my hobbies is I make guitars, and you can see down the bottom one of the guitars that I made on the left. I'll talk a bit more about those later. The guitar on the right, a Fender Telecaster, yes, absolutely, you could 3D print it, but it would be a stupid way to make it. Much better ways to machine it out of a block of wood, out of any material. You get better results, better quality all the way. The one on the left, you couldn't possibly make any other way. So that's what my second line is about. You know, complexity is great for additive manufacturing. The converse is true. If it's a simple part to make, so my rule of thumb is if you can make it on a 3-axis CNC milling machine, then it's probably not worth printing. So some examples of that complexity that we see a lot about. So the best known one, of course, or the very popular one, is topology optimization. So topology optimization is using mathematics to get rid of the material that's not doing anything useful. So if you looked at the table or the chair you're sitting on and did an FEA analysis of that, you find 30 to 60 to 90% of the material in the chair is not doing anything useful structurally. So the question becomes, can you get rid of it? If you get rid of it, it makes the product lighter. So what you see on screen there is a titanium bottle opener that's on my keychain. If you were to look at the conventional way, you'd start with a block of, in this case, let's say aluminium, you'd start with some billet aluminium, weigh around 10 grams. You'd cut away around 60% of that, and your final product would be the bottle opener you see in the middle, would weigh around 4 grams. In contrast, the topology optimized one, gram. Now think about that. That's a 90% weight saving over the original block of material. So the material savings can be enormous. So if weight saving is a big advantage, you think about airplanes, aeronautics, you think about race cars, then saving that weight is hugely valuable. The fuel savings in a year on an airplane, the difference between winning and losing a race of a few hundred grams. So again, another real world example, this is some University of Auckland students who did a startup on this. They're keen mountain bike, and I make and sell topology optimized brake calipers, and now they've also started doing brake discs for mountain bicycles. Now, mountain biking people are crazy people. They spend stupid amounts of money, which I don't understand, on bikes. So that's a perfect market. You know, it's not about how much it costs. It's about how much performance advantage it gives you. And in this case, saving those grams gives you that performance advantage. Another real world example that I was involved with a few years ago was for Atlas Copco, was for a hydraulic manifold for an underground drilling rig. So what you see there is one of these giant tractors that goes into mines underground and drills holes. I assume that's what it does. On the right side, you can see an extendable boom arm, and on the end of that, there's a hydraulic manifold, which is a block of material that takes hydraulic fluid from one place and distributes it to lots of other places. So this is what we're talking about. At the end of that boom arm, there's that block of steel. So that's how they make manifolds today. They take a block of material, drill a whole bunch of straight holes, plug some of the holes, and that forms an interconnecting network of pipes that takes the fluid where it needs to go. They needed to lightweight that because it's a boom arm that extends, they needed concrete counterweights on the back of the underground drilling rig. We redesigned it, going from 16 kilos to 1.4 kilos. So it's a 92% weight saving. That is huge, but it's not just the weight saving, it's the material saving. So again, this is a good example of design for additive manufacturing, because the first time we printed it, Atlas Copco said we want it printed in the orientation you see it there on screen, so vertically. The reason for that is they wanted better surface finish in the top where the valves go in, you know, seat in to the top. So when we first printed it, we printed it that way, and you can see all that support material. So support material in metal printing and in extrusion-based plastic printing is sacrificial material that you break away afterwards and throw away. So that was the amount of support material in it. As it turned out, we had to machine those seats anyways to give it the RA value, the surface finish tolerances that it needed. So we now redesigned the entire manifold to be printable the other way around, and it's now printable with basically no support material. So you cut it off the build platform when you're done, and the part is good and ready to use. In fact, even the threads are used as you see them there. They have copper bushings that provide the seal, so they don't even need to chase the threads to clean up the threads. And it provides an adequate seal. It's not the smoothest thread in the world, but it does work. So that's the finished manifold there. I'm holding it in my hand, so it gives you an idea of the size of it. The block of steel that makes it up, you cannot lift up with one hand. It's just that heavy. So as a complexity, and if any of you ever have the chance to come to New Zealand, the invitation is open. Come and visit our lab. You'll see everything in our lab is geometrically complex. We generally don't print simple parts. There are some exceptions that I'll talk about in a few minutes. The other big advantage is what we call mass customization. So making products that are customized for every user. So instead of mass manufacturing 100,000 products all the same, you manufacture 100,000 products where every product is custom made for you, the user. And of course, the prime application for that is anything medical that needs to fit our bodies. Perfect area of application. But what's interesting is look at some of the numbers on screen there. We're not talking small quantities. We're talking reasonably large quantities. So mass customization in medical is huge. And one of the areas we've been doing quite a bit of work on is prosthetics. So on the right, you see Nea, a 2.5-year-old girl missing the bottom half of her arm. So the way they make prosthetics today is you put your arm in plaster. Once it dries, they may have a negative. From the negative, they pour in material to make a positive, spend a few hours shaving it, filing it, making it right. It takes many hours and a lot of experienced craftsmanship. On the bottom left, you see a scan of Nea's arm, and you can actually see pen marks where the prosthesist has put marks saying this is important areas to avoid. We have a CAD model. We marry the CAD model with the scan model, subtract one from the other, and we then have a perfect socket that fits the patient perfectly. In the middle, you can see it with the myoelectric implants to pick up muscle movement. And on the right, she's wearing a passive prosthetic when she's running around the house and her parents didn't want to wearing a $10,000 bionic prosthetic. So that whole area of mass customization is great. And one that came up coincidentally about 3 months ago when COVID started was face masks. So face masks, most face masks, the cloth face masks don't seal your face properly. So a company called Bellis 3D came up with an application for your iPhone where you hold your iPhone out in front of you, you look to the left, you look to the right, and it generates a 3D scan of your face that you can see on screen there. Literally 10 seconds, you've got a scan of your face. And you'll see on the bottom right there, there's a bottom for a mask filter. And what that does is it automatically generates a custom mask filter that you can just put over your cloth mask to provide a good seal on the mask to make sure everything works right. And you can see when they're literally, less than 30 seconds, I had a mask ready to print, and I printed it on my little desktop printer at home, and it works great. So amazing example of that mass customization. The other third, so we've got complexity, mass customization, and then the other big one is part consolidation, taking a product that's made up of many, many simple parts and joining them together into one much more complex part. So this is related to complexity. And one of my favorite examples, and it's my favorite example because it's an example of heavy duty engineering. This is a gas turbine burner. I mean, this is about as extreme an engineering environment as you can think about. So Siemens now make these for production for a few years now. The original one made out of 13 machine parts welded together, brazed together, which means every one of those welds has to be inspected. Every component has to be inspected, and every weld has to be inspected. That's a lot of extra work. Because of the relatively inefficient cooling of straight holes for cooling, they needed a thermal barrier coating, so a coating at the top so it doesn't burn out. They then redesigned it for additive manufacturing down to a single part, so 13 down to 1. Because of conformal cooling channels now being able to get the cooling where it needs to go, they were also able to improve the cooling, get rid of the thermal barrier coating. The big difference here is the lead time, 26 weeks down to 3 weeks. I mean, that is an unbelievable saving. And that burner, this is it in operation after it's been in operation on an Eon gas turbine for a year. So it shows you real world applications. Additive certainly can be used the right way. Another big advantage that's been a lot of talk, particularly over the last 3 to 5 years, is the idea of on-demand manufacturing. So manufacturing things where you need them, when you need them, rather than shipping them around the world. So what we're talking about here is the supply chain. And what you see on screen now is the supply chain, I guess, before the Industrial Revolution. Whereas if I was a chair maker, well, I was the supply chain. I might go to the blacksmith in the village, do some bartering for some nails, and I'd sell my chairs to you guys, the rest of the village. And that would be it. The village on the other side of the hill, too far away. This is a supply chain of today. So today, if I want my chair, I drive to the local furniture store, buy it there. They get it trucked in from a port, a city somewhere, who get it, shipped in from China, wherever the stuff is made. That supply chain is enormous. So typical consumer products, less than 10% of the price of the product is the product. The other 90% is that supply chain. Yes, all the transport, but each one of these people needs to make a profit. So it's 5%, 10%, 30% margins. That's how they make their money. So imagine in the future, potentially being able to go back to that pre-industrial revolution supply chain, where now you walk into your furniture store with your memory stick of a chair you've designed, or you've bought the digital design, and you say, please print me this chair. You go have a cup of coffee, you come back later, and the chair is done. Now, of course, the technology is not quite there yet to do that today, but people are working on it like crazy. It's a huge area, and the big area today is spare parts. So rather than companies keeping warehouses full of spare parts, they manufacture them as needed, when needed. And you just look at some of the numbers, it's actually frightening. Just automotive industry alone, over $750 billion worth of spare parts sitting on shelves doing nothing useful at all. I mean, that's the important thing. Is you got 750 billion not doing useful work that it could be doing. Most of these companies, I mean, Tetra Pak in Sweden, for example, they've got a warehouse full of parts in Sweden. They say, you know, somewhere between 60 to 80% of those parts will get scrapped at the end of 20 years. They legally have to keep them for 20 years. Some of those parts are consumables. You know, say seals for machines they send out all the time. Other parts they never send out, but they have to keep them. So imagine being able to now get rid of all that inventory, keep a digital inventory, and make them not just when needed, but where needed. So instead of shipping them around the world, if you need a part in Japan, you have it manufactured in Japan. Yes, there are a lot of certification, qualification questions about that, but that is being worked on all around the world. So then the other big area, which to me, you know, from a creativity point of view, is one of the most exciting, is the innovation catalyst that additive manufacturing becomes, the way it allows you to very, very quickly test ideas. And another COVID-related one, so this was during COVID, a little video clip there if it works. I won't stay on it too long in case it interrupts the verse. This is a little emergency ventilator, so nothing special. It just replaces the hand of the doctor or the nurse that would otherwise be massaging the ambu bag. So it's not a ventilator, it's just something to help somebody get from one end of the hospital to the other, and it allows the doctor to do something more valuable than massage an ambu bag. The point with this is we went through 3 iterations in less than 2 weeks. So from the idea, first iteration sort of worked, not quite, do another iteration, then a third iteration, we had it working right in 3 weeks. And that is unbelievably valuable. Another example, this is Jenna McGill, one of my students from probably going back almost 8 or 9 years now. She's an avid mountain biker, and when she travels around, she's got a big cardboard box with a mountain bike in it that's too hard for her to get around. So as a third-year design project, she said, I know, I'll make a little set of clip-on wheels that you can clip onto any box. Really, really great idea. Now the wheels, you can go to your local hardware store, to Kmart, buy skateboard wheels, so no point printing those. But she printed the clips, and she did a really good design to make interlocking clips so they could be printed in the smallest possible volume. With 3D printing, as the volume goes up, the cost goes up exponentially. So if you can keep your volume small, big advantages in doing that. So a really nice example of idea realization. And I think my next example of that is to say something politically incorrect about Apple products. Design flaw on the Apple. The iPad in particular has got a design flaw that the speakers on the iPad are on the back of the iPad, which means the sound is going the wrong way. The sound is going away from you. So bass doesn't really matter because it's omnidirectional, goes in all directions. Treble, the high frequency sounds go straight out the back. So if you listen to voice in particular, if you listen to a movie, the voice is always a little bit bassy and a bit hard to see. Bigger problem in my case is I'm lying in bed watching a zombie movie and the sound is going straight towards my wife. So there were political reasons why I had to solve this problem. So I spent a few weeks, I had a post-it note stuck to my iPad, which sort of worked, but looked a bit unprofessional. So I designed a little clip-on iPad speaker. It's just a stupid little widget that you slide onto your iPad and it redirects the sound towards the front. But that ability to have a problem, try a few crazy ideas, they may not work, they may work. That's where 3D printing gives you an invaluable example. Of course, now I've got the iPad Pro, so I've had to put it on steroids and go quadraphonic because it's got 4 speakers on it. And that leads me to my example, my personal example of guitars, which I do as a hobby. So I started back in 2011 making 3D printed guitars, and really I did my first one purely to see if it could be done, to see if it was possible to print a real working electric guitar. And I did my first one, and I was amazed by how well it played, how well it sounded. And since then, it's turned into a little side business that I do as a hobby. I've just done number 86, and I'm working on 87 now. So about 73, 74 of them sold over the last, you know, sort of 8 or 9 years. And just to give you an example of some of them, again, all crazy shapes, internal shapes that would be impossible to make any other way. Because if I was going to make regular normal guitars, I wouldn't be 3D printing them. And it made sense because I was doing guitars and basses. It made sense to print the rest of the band. So I think I've done about 3 or 4 drum kits so far. I think 2 or 3 keyboards and 1 saxophone, which doesn't quite work yet. So I need another iteration to make that work properly. And the one just to the left of the saxophone, the Steampunk, just to show you what that does. This is a little video of it. So all the gears inside work. There's a little motor that rotates all the gears. Now, to hurt your brains, that whole guitar body printed in one piece, no assembly required. So all of those gears are printed, the piston all assembled, the powder between the moving parts, you blow it out when you're finished and you're good to go. And then one of my more recent ones, just to show you the Beatles theme bass. I'm a big fan of the Beatles. So I did a Beatles themed bass. It's the Höfner bass that Paul McCartney plays. It's sort of violin shaped bass. It's got the score for Yesterday on the front. And inside there's sort of iconic scenes from Abbey Road. I think I've got a close up there. There's the Abbey Road scene where they're walking across. There's the Sgt. Pepper's drum kit and so on. And I mean, it's a beautiful work, and my wife kindly painted all the inside bits with a little, with a paintbrush by hand. Unbelievable sort of labor of love to get that level of detail in. Yeah, that way. So this is what prompted me to make my latest guitar. So I think rather than spending all that time and effort painting them, could we print one in full color? So this is a Scarab, the latest one I've done. And what you see on screen there is as it comes out of the machine, printed in full color with that wood grain ready to go. The only thing I've added to it is I clear coated it. So I've sprayed it with clear lacquer just to protect it nicely. But that ability to print in clear is unbelievable. And in this case, the dragonfly wings, which are a bit hard to see on a big picture like that, the dragonfly wings are clear. Everything else printed in full color, ready to go. So as I said, this is a hobby project, but one that I enjoy doing, and it keeps my sort of creativity going, saying, what can I do next? I've done an alien themed one. Also, themed guitars are always a lot of fun. And sort of one of the, thoughts or one of the things I need to sort of point out really important, which is really related to that design for additive manufacturing. Earlier, when I talked about the manifold that we printed vertically with all that support material to play with, one of the key goals of design for additive manufacturing is to minimize the post-processing needed in additive manufacturing. So it's one of the big myths of additive manufacturing. When you have people from the companies manufacturing the machines, they paint a picture like you hit print and you get these magical polished parts coming off the machine. Unfortunately, that is not the case today, and won't be for the foreseeable future. Now, there's many people working on automating post-processing in various ways. So post-processing, what we mean by that is all the work you have to do after you print the parts. So something as simple as removing support material. For any of you who've used extrusion-based FDM printers, sort of MakerBot style printers, you will have learned the nightmare of removing support material, where you've got to break it off and you stab your hands while you're doing that. Polishing, machining, painting. So all my guitars, for example, were painted. That's extra work you have to do, that you have to take into the equation before you can actually sell your parts. And just to exemplify that, this is a project that TIDA, the Titanium Development Association, a company in New Zealand, did a few years ago. It was for a conference in 2013, an HVAC conference, where they printed little spanners to give to people, printed in titanium. And what you see there highlighted in yellow is support material that you've got to remove. You've got to break it off afterwards to get rid of it all. And that is a huge amount of labor. Now imagine doing 200 or 500 or 1,000 of these spanners. We had a team of student labor, luckily, that was able to remove all the support material, but it's something really important to take into account in the overall equation of doing what it is you're doing. And again, I'll give you one more example of that post-processing. And just to go back, from the Waller's report, we do a survey every year, and the pre and post-processing in metal AM, somewhere between 35 to 45% of the cost of a part is in pre and post-processing. So any design work you can do to minimize that post-processing is money in your pocket. So that manifold example I showed you earlier, by flipping it upside down and redesigning to have no support material, we saved a lot of money and a lot of time. This is one of the guitars that was on the slide earlier. This is the first guitar printed in aluminium. So it's the first, I think, in the world 3D printed metal guitar. And what you see there is the guitar still welded to the build plate. So it's the whole guitar. So printing in metal is a welding process because there's a huge amount of stress when you weld trying to curl the part up. The support material there is to anchor it to the hilt, to the print plate, and act as a heat sink to suck away the heat to prevent it from distorting. And just to show you a bit of a close-up, you can see the theme of the guitar is barbed wires along the top and the back, the front and the back of the guitar, and there's flowers, there's roses inside the guitar. And what you see there is all the support material separating the strands of barbed wire. And if you look closely, even in the flower, you can see the petals of the flowers with support material in them. That is a nightmare to remove. Now, for those of you who have experienced the joy of removing plastic material from an FDM printer, put that on steroids now and imagine doing that with metal material. Aluminium, relatively easy. In comparison, steel would be unbelievably difficult to remove. So to give you the final product, if I may say so, a relatively stunning guitar, very nice, one of my favorite ones, plays beautifully. The print time was actually not too bad because it's only 40 mil high and it was done on a 4 laser machine, 9 hours to print. The cooling, the heat treatment was probably a bit over the top. This is an artistic work, so it probably didn't need the 30 hours of heat treatment afterwards, but the big point here is the post-processing. I've printed 2 of these. The first one, it took me 4 days to remove the support material. My hands were bleeding by the end of it. And this is because on the first one, you don't know the best technique for removing the support material for that particular design. And remember, with additive manufacturing, chances are every design could be different, which means every design you've got to relearn how to remove that support material. And then another 4 days it took me of filing, sanding, shot peening to give it a beautiful surface finish, a really nice professional looking surface finish. The second guitar I did took me 2 days and 2 days, but that's still 4 days of expensive labor to get the guitar to the level where it needs to be a sellable product. So again, being able to minimize that effort is one of the big points of additive manufacturing. And it's probably one of the first rules. So the first, my general rules of design for additive manufacturing, the first step, get rid of all of the material you don't need. Material is, you know, the Achilles heel of additive manufacturing. The more material you have, the exponentially higher your print time goes. And I think I heard somebody describe it as the, you know, printing in metal or in plastic on industrial systems. It's the equivalent of painting your house with a Sharpie marker, with a little black marker. That's the time it takes. So any material you can remove saves you time, saves you money. And then the second step is try to design to avoid support material. So the golden rule is below a certain angle, depending on the metal, but generally it's at 45 degrees. Any angle below 45, you will need support. Any angle above 45, you don't need support. So you design to try to avoid angles below 45 and big flat surfaces. Once you get your head around that, it actually becomes relatively easy to design parts with no or minimal support material. So as I said, yeah, that design for additive manufacturing, absolutely critical if you want to use it for beyond prototyping, to make parts to sell to customers. So with all that marvelous world of 3D printing, and it is a wonderful technology, what's missing? Unquestionably, we need more materials. We have a dozen or so metals to choose from, a dozen or so polymers to choose from. We need more of them, unquestionably. Better surface finish. There's a surface swatch in the bottom center of that slide. Today, we're probably, and that's plastic and metal, we're probably in sort of the right-hand half of that surface roughness swatch. We need to be in the left-hand side before it becomes much more widely available, or we need to start to change people's aesthetic on what is an acceptable surface finish on product. I don't have an answer for it, but certainly better surface finishes are a requirement for wider adoption and certification. We need products that, we talked earlier about on-demand manufacturing, manufacturing parts around the world where they're needed. Well, to do that, you've got to be able to guarantee the part you get is of the right quality. So a lot of work going on around the world for that, but still a lot required before people trust the technology. Engineers in general are very conservative, so the more we can do that, the more it'll be adopted. Better design tools, absolutely. So we talked about topology optimization. There's some amazing tools coming out for lattice structures and gyroid structures. So N topology is a fantastic tool. We need more of those tools to make it easier for us as engineers and designers to get those products right. And really important to my mind is we need to update our engineering curricula to actually include design for additive manufacturing as part of design for X, you know, design for injection molded, design for whatever the manufacturing technology, additive manufacturing. It's just, you know, design for injection molding. The golden rule is you keep an even wall thickness everywhere. It's the same for additive manufacturing, but just that much more important, because if you don't, it becomes, yeah, too expensive to use. So really, I mean, you know, that was 30 minutes of my general thoughts on the importance of designing the right way for additive manufacturing. So I think I'll leave it at that, other than to give you my email address. So if any of you guys have got any questions, send me an email, feel free to contact me. And open invitation, as I said, if any of you are ever in New Zealand, feel free to drop by the lab. We run an open access policy. If we're there, the doors are open, and we encourage people to walk in just to wonder what's going on. So yeah, with that, as I said, feel free to email me. And I thank you very much for your time and hope to talk to you or see some of you again soon. So thank you.